Welcome guys, I'm DrAvitech. In this video, we're going to be deriving the Fourier series. So let us get started. So how all of this happened was French mathematician Jean-Baptiste Fourier was trying to solve a problem on heat conduction within a thin, long insulation rod. So he was trying to face a problem. No, he was facing a problem, not trying to face a problem. So the problem was he was trying to express functions as trigonometric series. Then he came up with a particular formula and said that if a function is periodic with within the interval minus L to L, this very interval, that very function can be written as an infinite sum of trigonometric series where we have a naught over 2 plus the sum from n equal to 1 to infinity of a sub n cos n pi x over L plus the sum from n equal 1 to infinity of b sub n sine n pi x over L. So this is what Fourier was trying to say, that we could write functions like this. Let me put a bracket here. So we could write functions like this. That's what he was trying to say. Also, this very function would be having coefficients that we need to solve for. So we have a naught, we have a sub n, we have b sub n. Now here's the thing, it's actually very easy to find. But before then, take it down a little. Let us slow down. Before then, let us slow down. This very period here is the period 2L. But first of all, I want to start solving this. I want to prove or derive this using the period 2 pi. And here's why. It is much more easier to derive with the period 2 pi. However, when the period is 2L, it is much more general because 2 pi can only solve equations involving periodic functions with 2 pi. Because when a function is no longer periodic with 2 pi, you cannot use these very ones that I'm about to derive. But I'm still going to give you the formula that you're going to use to derive functions whose period are not 2 pi. So let me rewrite this whole stuff. So when the period is now 2 pi, so f of x, then we have a naught over 2 plus the sum from n equal to 1 to infinity of a n cos nx plus the sum from n equal to 1 to infinity of bn sine nx. Now, as you can see, when the period is 2 pi, it is now gone. It's not kind of looking much more easier. There's no over L and the rest. So it's not kind of looking much more easier. They're actually similar, but it's looking easier. Remember to hit the subscribe button, like this video, and share it across to your classmates. Now let us proceed. So if you look at these very formulas, you will notice that we have coefficients. We have the coefficients a naught, we have a sub n, and we have b sub n. These are all coefficients. So we're trying to see how we can find them. But it's actually very easy. It's actually very easy. A naught is a constant term. A naught is a constant term. So A naught is equal, let us find A naught. So the first thing that Fourier did was to integrate every single thing over the period. Integrate every single thing over the period. So let's integrate from minus pi to pi of f of x dx. Also, we're going to integrate this from minus pi to pi a naught over 2 dx plus the sum from n equal to 1 to infinity. Then we're also going to integrate from minus pi to pi a sub n cos nx dx plus we're going to also say the sum from n equal to 1 to infinity b, the integral first. Integral from minus pi to pi b sub n sine nx. Okay, so we're trying to get our constant. That's what we're trying to do. So let's get our constant. So this is from minus pi to pi of f of x dx equal to, now if you notice, a naught over 2 is a constant because we're integrating with respect to x. So bring out the a naught over 2. So this is a naught over 2. Then we have minus pi to pi dx plus the a sub n here is a constant, so I can bring it out. So this is the sum from n equal to 1 to infinity of a n integral from minus pi to pi cos nx dx plus the sum from n equal to 1 to infinity. Same thing would happen here. B sub n comes out. Minus pi to pi. Oh, I didn't put dx. Sine nx dx. Now, if you look at this, this will be 0. Remember that I've done this in the previous video. The integral from minus pi to pi of cos nx is 0. So we've done this previously. Same thing here. The integral of this is still 0. We've done this in the previous video. Then the integral of this, okay, we have a naught over 2. The integral of this gave us 2 pi, if you remember. So we've been able to also do that. So this part will be remaining. The integral from minus pi to pi of f of x dx. So that's what we have. Now 2 we cancel out 2. 2 we cancel out 2. So what we'll be having left is the integral from minus pi to pi of f of x dx equal to pi a naught. So right now we're going to divide both sides by pi. So dividing both sides by pi, when you say over pi, just put 1 over pi here. So this is 1 over pi. Then we have the integral from minus pi to pi f of x dx equal to a naught. So that's your a naught. A naught is 1 over pi integral from minus pi to pi of f of x dx. That is a naught. So that's much more easier for us to find. That's much more easier for us to find. Now the significance of this, we're going to treat this very significant. It has an importance, this term here. Otherwise, you would be saying, why is it that we're trying to express in terms of trigonometric functions or series? And why is this constant term here? So we're just going to, for now, I'm going to discuss the importance of that. In electronics, we call that our DC component. But we're going to learn why we have that. So let us proceed to A sub n and B sub n. Let us find what they are. Now, for A sub n, if you notice, A sub n is with a cosine. Now, we're trying our best to make sure that we find every single coefficient here. Now, please listen. Please listen. If I am trying to find something, this is A sub n. Every single function has sine and cosine in them. That's what Fourier is saying. That when a function is periodic and when it's satisfied Dirichlet condition, did I pronounce that well? And it's actually satisfied that very condition. Let me see if I Dirichlet condition. Okay, so if it satisfies that and it has a Fourier series, then that very function will be having sine and cosine in it. So it's either we have a combination of both sine and cosine, or we have only sine and only cosine. And the thing is this, how do you then know if a function would have cosine? Very simple. This very coefficient here, A sub n, will tell us if there will be a cosine. So how would I get A sub n? There's actually an easy way to get A sub n. A sub n is equal, without derivation, I would explain why this is correct without derivation. 1 over pi integral from minus pi to pi of f of s cos nx dx. I'm still going to derive it, but let us look at this. Let us look at this carefully. A sub n is trying to find out how much cosine is embedded in a particular function. So here's the thing. You have a function f of x. You are trying your best to see, does this function have cosine inside of it? The best way to know about it is to multiply it by cosine. Because if I multiply something that has cos by cos again, I am going to be having cos squared, which is a larger expression. So when I do f of s and then I multiply by cos nx, I'm going to be having a much more larger expression. Now, if I have an answer here, if there's an answer, let me say some answer, maybe 1 over n squared pi squared. If I get an answer here, it means cosine was present in the function. But what if I have f of x sine nx? Now, remember that I said cosine was present in the function. But right now, if I should multiply a function that has only cosine embedded in it, and I go multiply with sine, my answer will be 0 because there is no sine in f of x. I hope you're getting it. So the reason for us to multiply with cosine is because cosine will tell us, oh, if this increases in its magnitude, if it doubles up or if it rises, that means the function itself is going to be having cosine in it. And then if it was supposed to be only a function with cosine, and then I multiply by sine, I'm going to have 0. But let me explain better. Let's derive it. Let's derive. So the first thing I want to do is to multiply every single thing here by cosine. Yeah, multiply every single thing here by cosine. Because the only way for me to be very, very sure that, oh, there's going to be a cosine in my function is when I multiply by cosine. Because that way, I'm going to be making the cosine much more visible. It's just like saying someone is, I think this is a weird reason, but someone is, I don't really want to use illness, but one of the ways to know something is to make it much more pronounced. So if a function is having cosine, one way for me to know that cosine is very present without me being told is to multiply by cosine again. So let me multiply by cosine because I'm going to be making the cosine much more big. Let me multiply every single thing here by cosine. So I have f of x cos, this is n already, so let me use m. So this is mx equal a naught over 2 cos mx plus the sum from n equal to 1, then a sub n cos mx cos nx plus the sum from n equal to 1 to infinity of b sub n sine mx. Oh, sorry, I'm multiplying every single thing by cos. So cos mx sine nx. Now, what have I just done? I've multiplied every single thing by cosine of mx. Now, remember, what am I trying to do? I am trying to find out the cosine content. The content of cosine, how embedded. So the portion of this thing that's going to be having cosine embedded in it, that's what I'm trying to find. So right now, after multiplying these things by cosine, what better way would I be able to know if cosine is embedded in a function is to take the integral of that very thing. So I'm going to integrate all of them. Dx, integrate, dx, integrate. Let me put the integral here. Dx, integrates, dx. So that's what I'm going to do. Beautiful. I'm going to just integrate every single thing. So let's proceed. Let's proceed. Now, this is going to remain the same. There's really nothing I can do here. This was the explanation I was trying to explain earlier. So this is integral from minus pi to pi f of s cos mx dx. Now, what will be the answer of this? If you look at this carefully, we know that a naught over 2 is a constant. A naught over 2 is a constant, so I can actually bring it outside. I can bring out a naught over 2. It can come outside, so that's not a problem. So if you integrate cos, what would you get? If you integrate cosine over this interval, we've done that in the previous video. If we should integrate this over this interval, you're going to get 0. Remember, right? You're going to get 0. So this is 0. That whole thing there is 0. Now I want to leave this one. Let me come here. What I'm trying to do here is this. Remember, the reason for me to multiply every single thing here by cosine is to know how much of cosine I have in a particular expression or a particular function. Now, if I am multiplying cos and sine together, these two things are different functions. My area will be 0 here. My area will be 0 here because cos and sine, none of them have, they're not the same. So this very part would be 0. Remember that we've actually treated the integral of this integral. So since cos and sine, none of them is contained in the other, my integral would be what? 0. Now let's come back to this because this is the only remaining item. Now cos and cos are now together. As you can see, the only way for me to have a double, remember, I multiplied everything here by cosine so that I can see how increased, how cosine is going to be much more pronounced in my expression. Now cosine will be pronounced here because cos times cos is cosine squared. But I cannot have a cosine squared if the m and the n are different. If the m and the n are different, I cannot be having my cosine squared. They can only be a cosine squared if the m and the n are the same. So if the m is equal to the n, because you cannot be having two different things giving you a square. They have to be exactly the same. So if these two things are exactly the same, I'll say let m equal to what? N, so that they will be the same. So it means this will be the sum from n equal to 1 to infinity of a sub n integral from, anywhere I see m, let me put n. So this first part, sorry, This m here will then become n because I am trying to make sure that all the m become n. So this is minus pi to pi cos this m here becomes n, and this is cos nx dx. Okay, so this is minus pi to pi f of s cos nx dx equal to the sum from n equal to 1 to infinity of a sub n. Now if you look at this, minus pi to pi, this times this will then give me cos squared nx dx. Now if you remember, we've done something like this before. In the previous video, we integrated cos squared nx. We did something like this. And when we did that, when we integrated this, we found out that the value of this was just pi. So this is the sum from n equal to 1 to infinity of a sub n pi. Now, because this expression no longer, this a sub n is going to be a number, the summation is already in the expression, there's no need for it to be here anymore. There's no need for this to be here anymore. So you could take this out. So we have the integral from minus pi to pi f of x cos nx dx. So that's what we have. So right now, this minus pi to pi f of x cos nx dx is equal to pi a sub n. It's equal to pi a sub n. So for us to get our a sub n, we're going to divide by what? Pi. So that means I have 1 over pi integral from minus pi to pi f of x cos nx dx equal to a sub n. So that was how they got that. So you can see, right? So following the same thing, for me to get my b sub n represents the sign content, the sign component. So right now, for us to get b sub n, we're going to have 1 over pi integral from minus pi to pi f of x. For me to know how much of sine I have in my expression, I'm going to multiply by sine. So sine nx dx. And that, ladies and gentlemen, are the coefficients. These are the coefficients. Now, please remember that these coefficients are having a period, or they can only be used when the period is 2 pi. They can only be used when the period is 2 pi. You can't use it if the period is not 2 pi. So now let's come back here. This is all we have. Now, please take note. There are misconceptions that are popular and a lot of misconception when it comes to the formulas for Fourier. Yeah. Jean-Baptiste Joseph Fourier. There are so many confusions. The first confusion is there's an over 2 here. Most persons would meet me and say, oh, how and why is there a minus an over 2 here? Because in their own textbook, there's no minus 2. Now, since there's no minus 2 in your own textbook, check properly. The 2 will be right here. Let me say that again. The reason I put this over 2 here is so that there can be a singularity in the way my formula appears, where I have 1 over pi, 1 over pi, 1 over pi. For textbooks that do not put the over 2 right here and put the over 2 here, this will then become 1 over 2 pi, 1 over pi, 1 over pi. So like I said, the formulas will still be the same. They are going to be equivalent to each other. Now, a much more general formula, because this formula would only work when the period is 2 pi. A much more general formula is the formula that contains L. So our f of x will be the one at the top, a naught over 2 plus the sum from n equal to 1 to infinity of a sub n cos n pi x over L plus the sum from n equal to 1 to infinity of b sub n sine n pi x over L. A much more general formula. So a naught will then become 1 over L from minus L to L of f of x dx. A sub n 1 over L minus L to L of f of s cos of n pi x over L dx. B sub n is 1 over L minus L to L of f of x sine n pi x over L dx, where L is half period, or you could say T over 2. So you can see that these formulas, this very one is much more, this very one here is much more general. This one can solve regardless of your period. This can be solved regardless of period. If I'll be saying your period as if it's period I'm talking about. Okay, so every single thing here is a general formula for Fourier, where L is half period. Now, if you notice, there are also some textbooks that prefer to use 1 over, in short, not even 1 over, they prefer to use 2 over t. I hope you know that 2 over t is same thing as using this very one. Let me explain. You have 1 over L there, right? 1 over L. So this is 1 over, what is our L? L is t over 2. So this over 2 goes to the top, so that now becomes 2 over t. So you see that most times it is just still the same formula. Mathematics, we don't lie in maths. Every single thing is the same. There can only be some manipulations, but they are all truth. Every single formula all connects. So that is the whole idea. Now, another thing is this. When you are finding or solving the Fourier series of a particular function, you first of all have to find all of these coefficients. You know what these coefficients are before finally putting them into the Fourier series expansion formula. That's what you do. And with this, I'm going to call this the end of the video. I'm going to see you in the next video because I'm going to start solving problems on Fourier series. I'll see you there. Bye.